Okay, thank you for the introduction. This is a joint work with Yuki, Satake, and Tachio Terauchi. I'm presenting a new refinement type system for verification of higher order and non-deterministic programs. Let me start with the background. Recent years witnessed advances in automated methods for verifying higher order functional programs for various classes of properties, including safety, non-termination, non-termination, and temporal properties. Where there, different techniques are used to verify the different classes of properties. However, they are hard to combine in a unified framework. So, we propose a new dependent refinement type system that can uniformly express and verify universal and existential branching properties of call by value, higher order, and non-deterministic programs. Universal properties we can verify include safety and termination, which ask if for any run of the given program, a certain fact is satisfied. By contrast, existential properties such as non-safety and non-termination ask if there is a run of the program which satisfies a certain fact. Our type system can seamlessly combine universal and existential reasoning. For example, we can prove non-safety via termination and non-termination via safety. Moreover, we can prove termination and non-termination simultaneously. We have also studied meta-theoretic properties of the type system. Thanks to having both modes of non-determinism, in our system, that complement of any type can be expressed as another type in the system. And also, we have proved soundness and relative completeness. Let's see our type system in more detail. Our system is based on dependent refinement types that are types equipped with predicates on program values. For example, this type is a type of non-negative integers. And this is the type of functions that take an integer x and, if terminated, return r not less than x. A refinement type system ensures that a type-checked expression behaves according to the type. However, only universal branching properties can be expressed in ordinary refinement type system. So, we extend dependent refinement types with these new features. The first one, qualified types are used to express universal and existential branching properties, as well as partial and total correctness properties. Qualified types are dependent refinement types annotated with two qualifiers, Q1 and Q2. Q1 specifies whether the expression being typed behaves according to the type for any or for some non-deterministic variation. Q2 specifies whether tau holds for all value obtained as the result of a variation, or there exists a final value for which tau holds. In other words, if Q2 is turned A, the variation diverges or tau is satisfied. And if Q2 is turned E, then the variation terminates and tau is satisfied. This is an example judgment, which means that for any non-deterministic variation of the expression E, if any integer u is obtained, then u is positive. By contrast, this judgment means that for some non-deterministic variation of E, there is integer u, some integer u is obtained and u is positive. Let me explain typing rules that involve qualified types. This is the rule for integer constant. Please note that this type is assigned to the integer constant because integer constant is a value whose evaluation never exhibit side effects like non-termination and non-determinism. We can assign these qualifiers. And we also have subtyping rules for converting qualified types. Please note that universal types can be converted to existential types, and total correctness types can be converted to partial correctness types. This is the rule for typing red bindings. Because the expressions E1 and E2 are executed sequentially, we require that the qualifiers of the type of E1 and E2 coincide. And this is the rule for assigning partial correctness type to a recursive function. Actually, this is a standard one, which is adapted from previous work. And this is the one for total correctness. To ensure the termination of f, recursive function f, recursive occurrences of f in the body E is required to have the type tau rec, which has a recursion guard, which represents a well-founded relation between the argument x of f and x prime, the argument x prime of recursive cores, thus witnessing the termination of f. Our type system checks that the recursion guard is satisfied at all the recursive core sites. For example, let us consider this example. We can assign this total correctness type to the function sum. For the recursive occurrences of sum in the body, we assume this type, we assume that sum has this type with a recursion guard that witnesses the termination, conditional termination of the summation function. Okay, let me next explain the second feature called qualified bindings, which is introduced to cope with non-determinism from program inputs. Well, qualified bindings occur in type environments under argument of dependent function types. The qualifier Q specifies whether a certain fact must hold for any input or some input x that satisfy the type tau. For example, this type is the functions represent functions that for any integer x, for any run with the argument x, return some integer u, which is greater than x. Okay? By contrast, this type represents a function that there exists an integer argument x such that the function behaves according to this type, return type. For reasoning about existential bindings, we use the scoramization technique formalized as this typing rule. Here, please note that the existential binding is replaced with universal binding, followed by a scoramization predicate, phi. Let me use this example to explain the intuition behind the rule. This judgment says that for any x, integer x, and there exists an integer y such that x plus y equals 0. Here, by using this rule, the existential binding is replaced with the universal binding here, followed by this scoramization predicate. Please note that this predicate is sufficient to show that x plus y equals 0. And please note that, for soundness, we also need to check that the score minimization predicate is not empty. In other words, we check that for any integer x, there exists y, such that this predicate is satisfied. Okay, this is the rule for typing non-deterministic choice. Please note that the qualifier of binding Q1 is required to coincide with the first qualifier of the type of the expression. And we can drive this judgment. And we also have typing rules for function applications. This is the rule for universal bindings. This is actually a standard one adapted from previous work. And this is newly introduced rule for existential bindings. This rule checks that for any value x satisfying the type tau, there is a variation for existentially bound variables in gamma such that V2 becomes equivalent to x. This is complex rule. I will explain this example to use this example to explain the intuition behind this rule. Suppose that f has this type, which means this means that there is an integer argument x such that f has a diverging run. And we can assign the return type to f of y intuitively because we can generate any integer and bound y with that value and evaluate fy. Such a surjectivity is checked by this antecedent. We also have rules for converting function types for all to for exist, and for exist and exist for. I will skip the expression of these rules. Please refer to our paper or slides available from my webpage. And our type system also have features called gated encoding and guarded intersection types, which are introduced to achieve relative completeness. I will skip explanation of these features, but instead I want to explain how to seamlessly combine universal and existential reasoning in our type system. For preparation, I want to introduce complement types. Thanks to having both modes of non-determinism, the type complement operator can be defined like this. Please note that the complement of qualified types can be obtained by negating tau and negating qualifiers. Also, we can obtain the complement of function type by negating the qualifier and negating the return type. This is an example of complement types. Here, sigma represents the type of function that for any integer x and for any run with the argument x, the function diverge or return an integer u equivalent to x. The complement of sigma can be obtained like this. And this type represents functions that for some integer x and for some run with the argument x, terminate and return an integer u, which is different from x. Okay. And let me now explain how to prove non-safety via termination in a type system. For example, let us consider this problem. Our goal is to prove that this program violates this safety property. a naive approach to prove this one is to use a state space exploration technique. However, that naive approach would go through 1 billion recursive calls to discover a path violating the property. So instead, we use termination to prove this property. We first reduce this problem to the problem proving that this program satisfies the complement of the safety property. This can be expressed like this in a system. And then we analyze F, and we show that F is conditionally terminating. Actually, this well-founded relation witnessed that F has this total correctness type with the condition. And then we next show that the actual code to F always terminates by checking that the actual arguments satisfy the condition. And finally, we show that for any integer r returned by F, we can choose an integer z such that z plus r satisfy this property. Okay? And we are done proving it. And this slide summarizes our contributions. And future work include extensions with temporal specifications and advanced language features. Another interesting direction is to automate type checking and type inference. Okay, this is the end of my talk. Thank you for attention.
So we have plenty of time for questions. So the first question, online question is, can you extend your type system to effects, to express side effects?
To express side effects? Well, could you side
can
effects?
You extend this type system to cover
side
effects? Yeah.
What kind of side effect?
Let's say reference.
Reference. Okay. Actually, we are working on that. We are combining separation logic idea with refinement type system to handle references.
Okay.
Hi, good. Great work. Is being a non-deterministic essential to your framework? I mean, excluding non-determinism type system is still sound and relatively complete?
Well, excluding non-determinism from our
from
system,
your language,
which result in our POPL'18 paper. And we extended the relative completeness result in our POPL'13 paper to non-determinism in this paper.
And I have one more.
Yeah, go ahead.
What is the relation to the Naoki Kobayashi and Davide Sangiorgi of a CAHAB 2008 paper about lock freedom? So they, to prove the total lock freedom, they also proposed a hybrid type system, what they call, in which they do a semantic reasoning of a deadlock freedom inside.
Oh, so actually, I'm not aware of that, so I cannot answer your question.
So the next question online is, what is the model that your refinement type system is complete with respect to? You said your refinement type system is complete. What model it's with respect to?
Okay, what model? We define denotation semantics. Yeah, with respect, our type system is complete with respect to operation semantics.
Okay.
Yeah.
That's good. Sure.
So I have a question about the future work. So you mentioned about the extension of the non-width, the feature of the non-width, the probabilistic choice.
Okay.
Here, actually, so the first question is my mind. That's so how do you express the semantic of the probabilistic choice expression in the language? Because, for example, here we have to reason about the probability, right? So, for example, with the probability P, so the expression have the type the one with probability other probability, so it maybe have a different style. So.
Well, I'm sorry, I'm not actually familiar with probabilistic programming, and so I want to collaborate with some expert in this field yeah. Sorry, I have no answer now.
So can you compare the expressiveness of your system with, say, higher order logic?
Higher order logic. Okay, actually, we think that our type inference problem can be reduced to first order Hom cross solving problems by encoding higher order functions as integers. And I think it is also possible to reduce our type inference problem to higher order Hom cross solving, but I think currently solvers for higher order Hom cross are not available, so yeah, we are trying to reduce inference problem to first order Hom cross solving problems. Yeah.
Okay, so the next question. Can you move your slide to slide 11?
11.
Yeah.
This one?
Yeah. Okay. There might be executions that terminate and others that don't serve. You know, in this case, you know, some execution terminates, others don't. So this exists not enough for expressing termination.
Mm-hmm. Sorry, this means that for all non-deterministic evaluation terminates and the final value is equivalent to n.
So is this really mean total correctness or no? Oh.
This means total correctness.
Okay.
This type says that the expression, evaluation of the expression terminates, and then the final value satisfies this predicate. It is total correctness.
Okay. For every evaluation,
yeah, the first
there will
part
be some value.
Okay.
This one, but there will be other ones that may not.
Oh, sorry. Our language only have one value.
Okay.
Yeah.
Yeah, go ahead.
So you used a different one quantifier to quantify over the inputs to the function and another quantifier for the non-determinism. But why couldn't you have modeled the non-determinism as another input to the function? What is fundamentally different?
I'm sorry, could you repeat the question?
So non-determinism could be modeled as another input to the function.
Non-determinism could be modeled
as another input to the function.
Okay.
So a non-deterministic function you can think of as a function that gets the input and all the coin tosses, or all the non-deterministic values as an input. But your type system does have three quantifiers, so I imagine that really there is something fundamentally different.
That is because we have non-deterministic choice, this one, sorry, as a primitive. I'm sorry. We have non-deterministic choice expression, let x equals star in E. Oh.
Yeah, we have to see that.
This one, yeah. In example, we have this one. Let z, I'm sorry. We have, in this example, please see the let z equal star in z plus r, which non-deterministically generate an integer. To handle this one, we need additional qualifier. in the type.
All right. Let's thank the speaker again, and this concludes this session.
Thank you.